Alright, since last time we have an initialized logical device and a command queue here, and we even have a surface to present images on. So are we ready to draw things on the screen? Well, not by a long shot actually. In fact, there's still quite a lot of setting up we have to do before even clearing the screen with some color. So yeah, that's Vulkan for you. And the next big and important concept to understand is the swap chain. So what is Swapchain? Well, conceptually, it's a chain of images that we draw our final output onto. But why would we need more than a single image? And this has to do with how images are being presented on a monitor surface, actually. Normally, it's done line by line, right? And that takes some time, depending on your refresh rate of your monitor. And during that time, it would be nice for us to not to wait and start rendering the next frame already. So if we have not one, but more target images available, we can just acquire the next one, draw onto it, and then swap the currently presented one with a new one. Now, simply swapping an image that is currently being presented can result in the tearing effect, when one part of the pixels on the monitor is showing the previous frame and another part the current one. And to avoid this, the presentation engine can block the swapping until the current image is fully presented. And this is called vsync. I believe V is for vertical, since we synchronize the image swapping with a moment when the monitor has presented the full image, which I believe is called vblank. Now, what if we manage to render two or more images while a previous one is still being presented? Well, for starters, we of course need this amount of images available in the first place. And then there can be multiple strategies for dealing with the image chain. This is called present modes, and there is a number of those with their own pros and cons, but let's worry about this later. Hopefully this brief explanation gives the idea of what Swapchain is and why it's called like that. But yeah, thankfully in Vulkan there's a standard KHR extension that implements all this stuff, and we just need to create and use it properly. So let's proceed with that. But before that, there is one tiny thing that we need to do. We need to load more Vulkan API procedures that are provided by the device that we configure here. So in the create device function, right after we actually create a device, let's add the load proc addresses device call and pass our device to it. This will initialize another batch of crucial methods, including this acquire next image KHR procedure that acquires images from the swap chain. Let's also assert that one of those crucial functions like begin command buffer that we're gonna use is not nil after this call, because if something goes horribly wrong, this assert will tell us about this. Alright, let's proceed with the swap chain initialization, and as I said, this functionality is part of the official extension rather than part of the core Vulkan. So we need to enable this extension. And this extension is device-specific extension, not a global instance one. So we pass it to this device create info structure. And we can actually see that this extension is supported by the device in the Vulkan caps viewer here, VK KHR swap chain. This is the one that we need. Now, enabling the device extensions is really similar to instance extensions. There is the enabled extension count and the extension names pointer in the create infrastructure. So we will just create a slice like this and pass it to the device create info, just like this. Now for the swap chain extension, there's also a constant that we can use, KHR swap chain extension name, which is again just a string with the same name that we saw in the caps viewer. Now we can go back to our main function, and after creating the device, we can add create swap chain call and also defer the swap chain destruction. Now let's create those procedures. So let's see, to create the swap chain, we of course use the vk create swap chain KHR procedure, just like this, wrap it in vk check already. So that needs a device, the create info, the same allocation callbacks, and the result pointer. So let's add a global field for that. Again, pretty straightforward, vk swap chain KHR. Now we just need to fill out this swap chain create info. And this is the swapchain create info KHR structure, of course, with a fitting S type. And let's take a look at it. So you see, it's actually quite a large structure. It takes the surface to create a swapchain for, because of course we are presenting to a specific surface with a specific swapchain. Then we can specify the minimum image count that we want to have. Then we also need to specify the formats and the color space. We'll touch this a bit later. The image extent is basically the size of the images that you want. The array layers is normally 1 if you just present on a normal monitor, but if you are doing VR, for example, that might be 2 for each eye, I think. Then you will specify the usage flags for an image, which is a whole another topic that we are gonna cover. Then this sharing mode is about sharing the resource between different queues. In our simple example, we can ignore this because we have just a single queue, and by default it is exclusive. So the swap chain will be exclusive to that specific queue, so we will not dig into that. And this queue family index count and queue family indices is actually related to the sharing, so we can also ignore that. This pre-transform is about screen orientation, commonly found in mobile devices, for example. So there is like identity or some rotation or mirroring. We will fill that as well. Then the composite alpha is basically how the image is supposed to be composed onto other windows. For example, if you want to support some kind of semi-transparent windows, I guess you will need to deal with that. But by default this will be opaque, so we're gonna also specify that explicitly later. And the present mode is what I was talking about. There is an immediate mode. That means that whenever we present an image, the image that is currently being presented by the monitor will be immediately swapped by the new one, so you get a potential tearing effect. Then the FIFO, which is like just a queue of images. And then there's mailbox, which basically means that if there's an image waiting for the vsync and we provide the new one, the old one will be replaced by the new one instead of the new one being added to the queue. And there are some more, but I guess this is not very important now. You can read about them in the spec, of course. And then there's this clipped flag, which basically means whether the driver is allowed to not draw on the areas that are, for example, obscured by different windows and such. So probably it's a good idea to set this to true. And then the old swap chain is something that you can pass if you recreate the swap chain, which is something that you have to do if you resize the window, for example. And if you provide the old swap chain, this will allow the driver to reuse some resources. So yeah, let's start filling this out. The surface is just the surface that we created before, stored in G surface. Now for this min image count, the value that we normally want to have is 3, because there's normally one image that is currently being presented, another image that was submitted and waiting for the vsync to be presented next, and then we want to have an image that we are rendering onto. So this is what is called triple buffering, and it's something that we would like to have. However, the surface might impose some limits on that. So we actually need to check how many images a surface supports. For example, here in Vulkan Caps Viewer, we can see that my surface here supports the minimum image count of 2 and the maximum image count of 8. So we can use 3 images, but some other device could have some other counts. So what we should do is query the surface capabilities and clamp our desired image count to these values. So how do we do this? Let's introduce a local variable for image count, just like this, a utility2 variable, and we assign it to the min image count. Now ideally we want this value to be 3, right? So let's assign it here. But also we want to get the surface capabilities and do the clamping. For that we can use this get physical device surface capabilities KHR procedure that takes our physical device that we have, then the surface that we are rendering onto, and the pointer to the result of the capability structure. Something like this. Wrap the function with vkcheck. So you see the surface capability structure contains this min and max image count, which is exactly what we need for clamping this value. If for some reason the minimum image count for our surface is more than 3, then we want to use that value, of course. So we just take the maximum out of those two, right? Now the upper bound max image count can be 0, which means that the number of images is unlimited. But if it is defined, so non-zero, and for some reason it's less than 3, we want to clamp on that value as well, right? So let's add a check for that. Something like this, right? So if it's non-zero, so if it's defined, then we limit our image count by this max image count. Now let's proceed with the image format and color space. So this is something that we can also see in the caps viewer in the surface formats list. And you can see that the format and the color spaces that are supported by this particular surface are defined here. And this also depends on your monitor more or less. Like if you have a monitor that supports HDR, for example, you might have some more formats and color spaces. And the most widespread format, I would say, is this B8, G8, R8, A8. So it's not RGB, but actually BGR image format. I think there are some historical reasons for that, and this is how hardware works. So it's a go-to format for presenting. But also you see that my machine supports also RGBA and whatever this is. And then there is this UNorm and sRGB postfixes, which has to do with the gamma correction actually. And I will not really explain gamma correction here. I have an SDL GPU video about this topic where I try to explain it in layman terms. But basically, if you have an sRGB output format, that means that you write linear values to it and the driver will automatically apply the gamma correction to the values before presenting it. So we can afford not to care about this in our shaders, for example, while UNorm will not apply this gamma correction. So that's the difference. And for the color space, as you can see, it's all sRGB nonlinear in all the available formats here. So that basically means that the Swapchain image will be encoded according to the sRGB format, and nonlinear basically means gamma corrected, right? So what do we do with that? So let's say that we don't want to do any gamma correction ourselves, so we want to have this format sRGB, right? We want to prefer this, but we actually want to check if it's really supported. So we want to query the surface formats from our physical device, and then we are gonna check if it supports this one. If it doesn't, well, we just fall back to the first supported format, because there must be at least one. For your particular use case, you might want, of course, to have a more sophisticated algorithm, but this is what I'm gonna roll with for now. So querying the supported surface formats is done with this getPhysicalDevice surface formats KHR procedure that takes the physical device, the surface, and then it follows the same pattern as other enumeration functions. So you first call it with a pointer to the count to get the count, you allocate some array, and then you call it for the second time to fill the array, right? Nothing new at this point for us, right? Like this. We have a local variable. We also wrap the function into invkcheck. We allocate a temporary slice with surface formats KHR, and we call the function for the second time, providing the pointer to the slice data. We can even print the formats that are supported. And you can see that I'm getting all the same values as I saw in the caps viewer, right? So let's just choose one format. Let's have the first as a fallback by default, but then iterate over surface formats and try to find the BGRA sRGB nonlinear format, right? Just like this, right? It's a structure with two fields, right? The first is the format, the second is the color space, so we can compare it like this. So if it's this one, then we choose this one and break out of the loop, otherwise we proceed with more candidates. So now we can use the surface format for creating the swap chain. So image format is surface format, and image color space is surface format color space. Now let's talk about image extent. So the image extent is basically the size of your frame buffer, right, of your window. And there is some complexity about handling that. For example, if you look at the surface capability structure, you can see that there is a minimum and maximum extents, and then there's also the current extent that will be reported. And also the current extent might have a special value of max int, and in both width and height, which basically means that you got to figure out which extent to use within the min and max, right? And then the max can be 0 if the window is minimized and whatnot. I'd say for now, let's not really care about this and just get the numbers from GLFW for our window and just pass it here. Right, we can use the getFrameBuffer size, which will give us a size in pixels, which is exactly what we want for our images. And we'll just pass it here as image extent, width and height. Don't forget to convert it to U32 because GLFW returns I32, right? So in general, we need to handle this more carefully, as I said, because the window size can change and there might be some limits on the image extents, and you have to deal with full screen in specific ways and stuff like that. But for now, let's ignore this. And let's get back in our Swapchain create info. So, as I mentioned, the array layers is normally 1 for standard monitors. It's also available in surface capabilities, max image array layers of 1, right? For stereoscopic rendering, like VR or whatnot, this can be 2. Maybe there are more, I don't know, but 1 is a safe bet for usual monitors. Now for the image usage, let's take a look at which flags are supported. And what we specify here basically depends on how are we gonna use this image. And we can use this image in a number of different ways. The most simple one is use it as a color attachment, so we draw directly into a Swapchain image. For this we would just specify the color attachment usage. Another option would be to have our Swapchain as a transfer destination. If we were to render on some off-screen images, then do some post-processing maybe, and then just simply copy the data from our off-screen images into Swapchain images, we would use the transfer destination usage. Also, you can use this image as a storage image if you want to modify data directly in a compute shader or whatnot, but for now let's stick with a color attachment. So we specify the bit set with a color attachment bit set. Now for the sharing mode, as I said, we have just one queue. We can afford not to care about sharing for now, so we will leave everything as default, so exclusive, and we don't care about the queue family indices here, because those are for concurrent sharing. Now the pre-transform, as I mentioned, is about rotating screens and different orientations. We can also see in the capabilities viewer that actually the only supported transform for my case is the identity. But actually, if we take a look at our surface capabilities that we just queried, there is the current transform field that will contain the current transform, right, for the surface, which in my case will always be identity. So we can just use that. Now for the composite alpha, as I mentioned, let's just use opaque and not care about semi-transparent windows. And ideally, you should actually also check the surface capabilities for the supported composite alpha and choose the one that is supported, but I'm pretty sure that opaque is always supported. Now for the present mode, as I described, there are a bunch of them and they have different pros and cons. And this is something that might be worth having a setting in your game for. But I will just use mailbox for now, so that means that the queued image will be replaced with a newly rendered image. So basically we will always have just one image in the queue for presenting, which is good for lowering the latency. Now clipped can be true, which means that the driver will be allowed to discard any rendering operations for obscured parts of the window. And the old Swapchain is something that we will not care about for now. And yeah, this composite alpha has to be a bit mask value, right? So let's wrap this in a bit set syntax. And that should be enough to actually create the Swapchain already. Now let's add Swapchain destruction in the destroy Swapchain function. Just like this, we pass the device, the Swapchain, and the same allocators. And let's run the application and see if we get any errors. Nope, so far so good, all clear. So I think that's a good enough milestone for now. We have the Swapchain initialized properly. Of course, we are still very far away from actually drawing stuff. In the next chapter, we are gonna explore actually acquiring and presenting Swapchain images, because that's also a quite involved topic that also introduces some asynchrony and synchronization concerns, so this will be fun. But for now, stay tuned.